Right now, somewhere in the deep Pacific Ocean, a sound is traveling through the water. It has been traveling for hours. It will keep traveling for days. No ship made it. No earthquake caused it. No animal we have ever identified could produce it. Scientists have been recording it for decades. They have analyzed it with every tool available. They have compared it against every known source of acoustic energy in the ocean. They still do not know what it is. The ocean is not silent. It never was. But what lives inside its sound is something far stranger than anyone expected, and the deeper we listen, the less we understand. If you enjoy drifting into the deep ocean and discovering what lies beneath, please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. Sound moves differently in water. This is not a small difference. This is not a minor technical footnote you can set aside and forget. It changes everything about what the ocean is capable of, and it changes everything about why what happens inside it has stayed hidden for so long. In air, sound travels at roughly 343 meters per second, fast enough to cross a large room before you finish blinking. Fast enough that when you hear thunder rolling across a flat landscape, you count the seconds and calculate the storm's distance. Sound in air is local. It belongs to the space immediately around you. It fades as it moves outward. It scatters against surfaces. It loses energy to the medium it travels through. Eventually, it dies. In water, sound travels at nearly 1,500 meters per second, more than 4 times faster. But speed is only the beginning of the difference, and in some ways, speed is the least important part. In water, sound does not simply travel faster. It travels farther. It travels in ways that defy every intuition built from a lifetime of living in air, breathing air, moving through air, speaking into air, and hearing air in return. A sound made in the ocean does not fade the way a sound made on land fades. It does not scatter the same way. It does not lose energy at anything like the same rate. It can travel hundreds of kilometers. It can travel thousands. Under the right conditions, the specific conditions that exist in a particular layer of the ocean that scientists have studied for decades, a sound made on one side of the Pacific Ocean can be detected by a sensitive instrument. On the other side, not a faint whisper barely distinguishable from background noise, not a degraded, distorted ghost of the original signal. A clear, structured, recognizable acoustic event arriving at a sensor that sits thousands of kilometers from where the sound began. The reason for this is a structure that exists inside the ocean itself. A layer of water sitting at a specific depth. The exact depth varies by location and season, but falls roughly between 600 and 1,200 meters in most of the world's ocean, where temperature and pressure combine in a way that creates an acoustic lens. In this layer, sound that enters it from above or below bends back toward the center rather than continuing outward. It is trapped. It channels horizontally across enormous distances with almost no loss of energy, guided by the physics of refraction in a medium whose acoustic properties change with depth in just the right way to keep the sound moving along a path rather than spreading in all directions. Scientists call it the SOFAR channel, sound fixing and ranging. The name is functional and a little dry, which is unfortunate because what it describes is one of the most extraordinary acoustic structures in the natural world, an invisible highway running through the deep ocean, carrying sound across ocean basins, existing in every ocean on the planet, operating continuously, ancient, and until the middle of the 20th century, completely unknown to science. The SOFAR channel had been there for as long as the ocean had been there. Sound had been traveling through it for hundreds of millions of years. Animals had been using it. Blue whales are believed to have evolved their characteristically low-frequency calls specifically because those frequencies propagate most efficiently inside the channel, allowing a single animal to communicate with other members of its species across distances that would be impossible in any other medium. The channel was not created by human activity. It was not new when scientists discovered it. It existed, fully formed, doing exactly what it has always done before the first human being stood on a coastline and heard waves. We just did not know it was there. The discovery came in the 1940s. Through military research, scientists testing underwater explosions noticed that the sounds traveled far further than the models predicted, that the acoustic energy was being channeled in ways that the standard propagation equations did not account for. They investigated. They identified the thermal structure responsible. They began to understand the physics. And they immediately grasped the military implications. In 1949, the United States Navy began constructing a network of hydrophones, sensitive underwater microphones, specifically designed to exploit the SOFAR channel. The network was called SOSUS, Sound Surveillance System. Hydrophones were placed at the depth of the SOFAR channel at locations across the Atlantic and Pacific, connected by cables to shore-based processing stations where analysts could listen to the acoustic traffic of the deep ocean in something close to real time. The official purpose was unambiguous: detect Soviet submarines. The Cold War was beginning. Submarine-launched ballistic missiles were becoming a primary strategic concern for both sides. Being able to track Soviet submarines moving through the Atlantic and Pacific would provide an enormous military advantage. SOSUS was designed to provide that advantage. The microphones were extraordinarily sensitive. The processing was sophisticated for its era. The coverage was extensive enough that almost any submarine transiting the major ocean basins would be detectable. And for decades, the recordings that came in from the SOFAR channel were heard by military analysts and no one else. The entire program was classified. The data was not shared. The ocean's acoustic secrets, which SOSUS was capturing continuously, belonged to the Navy. When the Cold War ended, things changed. In the early 1990s, with the Soviet threat diminished and the strategic rationale for tight classification weakened, portions of the SOSUS network were declassified and made available to civilian researchers. Oceanographers who had spent careers trying to understand the ocean's acoustic environment with limited, undersensitive instruments suddenly had access to decades of recordings from the most capable monitoring network ever built, deployed in exactly the part of the ocean, the SOFAR channel, where acoustic signals from anywhere in the ocean arrived. They sat down with decades of audio. They began to listen, And almost immediately, they started hearing things no one had expected. Things that were not submarines, things that were not ships, things that were not the ordinary noise of ocean traffic and surface weather that formed the expected background of any long-term acoustic record. Things that were not anything in any existing catalog of known ocean sounds. Some of what they found had explanations. The ocean is an extraordinarily noisy place, and much of what SOSUS had been faithfully recording for decades was simply the result of physics. The cracking and groaning of sea ice in Antarctica and the Arctic, transmitted through the SOFAR channel across tens of thousands of kilometers. Underwater earthquakes sending shock waves through the ocean at seismic frequencies, detectable across ocean basins. Rain hitting the surface from above, generating acoustic energy that propagated downward into the channel. The collective sound of billions of snapping shrimp, a phenomenon called snapping shrimp noise, produced by cavitation as the animals snap their claws shut, loud enough in some regions to interfere with sonar equipment and audible in recordings from thousands of kilometers away. Strange sounds to human ears, accustomed to the acoustic environment of air, but explainable sounds. Sounds that had identifiable sources and understood mechanisms. Others did not. The unexplained signals in the SOSUS archive were not rare anomalies at the edge of the detection threshold. They were not faint disturbances that might have been instrument artifacts or processing errors. They appeared regularly, with enough amplitude and consistency that they were unambiguous acoustic events, real sounds, produced by real processes, detectable by real instruments at real distances. They had been recorded multiple times, in some cases over many years. They had been compared against every known acoustic source in the ocean, and they did not match. This is the scale of what the ocean had been hiding inside its sound. Not in the unmonitored depths beyond the reach of any instrument. Not in the theoretical spaces where we knew nothing. Inside the most extensive, most sensitive acoustic monitoring network ever deployed, which had been recording the ocean continuously for decades, there were sounds that nobody could explain. This is where the story of what the ocean says and what we do not understand about it actually begins. In the summer of 1997, the same year that NOAA's civilian access to the SOSUS network and its successors was generating new research at an accelerating pace, the hydrophone array picked up an extraordinarily powerful signal from somewhere in the South Pacific. The sound lasted approximately 1 minute. It rose in frequency as it progressed, moving from lower tones to higher ones in a sustained, sweeping arc. The overall shape of its acoustic profile, when rendered on a spectrogram, was distinctive enough that researchers could immediately recognize it as a coherent event rather than geological noise. It was loud enough to be detected by sensors separated by more than 5,000 kilometers. To put that in perspective, 5,000 kilometers is roughly the distance from London to New York. One sound, produced at a single location, simultaneously audible to instruments placed at opposite ends of one of the world's major ocean basins. They called it the upsweep. It became clear, as researchers examined the archive, that the upsweep was not new. Recordings going back to 1991 contained the same signal, the same sweeping frequency rise, the same approximate source location, the same extraordinary reach across the SOFAR channel. The array had been recording it for years before anyone looked closely enough to notice. It appeared to peak in spring and autumn, suggesting some kind of seasonal pattern in whatever process produced it. Its source appeared to be somewhere near the Pacific Antarctic Ridge, a region of significant volcanic and seismic activity running along the boundary between tectonic plates at the bottom of the Southern Ocean. The leading hypothesis was volcanic. Something about the interaction of magma with seawater, or the movement of volcanic gases through cracks in the seafloor, or the resonance of submarine volcanic chambers, one of these processes, or some combination of them, was proposed as the likely mechanism. But no specific mechanism has been identified that fully accounts for the upsweep's acoustic profile. The frequency sweep is not consistent with standard volcanic tremor signatures. The seasonal pattern does not correspond clearly to any known cycle in volcanic activity at the proposed source region. Attempts to correlate upsweep detections with specific seismic or volcanic events in the Pacific Antarctic Ridge region have produced suggestive but not definitive results. The upsweep has been recorded every year for more than 3 decades now. It rises in spring. It fades in winter. It rises again. From somewhere in the dark, something keeps making the same sound on the same schedule for reasons that remain unconfirmed. But the upsweep, strange as it is not the most discussed unexplained sound in the SOSUS archive. That distinction belongs to something recorded a few months later, in the summer of 1997, from a different part of the Pacific. The signal came from the eastern equatorial Pacific. It was extraordinarily powerful. Powerful enough to be detected across the entire Pacific basin. Audible to sensors spanning the width of the world's largest ocean. Unlike the upsweep, it did not rise in frequency. It did not sweep. It was brief, lasting less than a minute, and its acoustic profile was complex in a way that immediately distinguished it from geological noise. The frequency contour of the signal, when rendered on a spectrogram, rose and fell in a pattern that suggested something biological rather than geological. But nothing biological should have been loud enough to produce it. The analysts who first listened to the recording named it based on the sound it made when played back through speakers at a speed that shifted it into the range of human hearing. They called it the bloop. The bloop became, in the years that followed, the most publicly discussed unexplained ocean sound in history. Its acoustic profile was unlike any known geological process. It was unlike any known atmospheric event, and it was, most provocatively, unlike any known animal. The blue whale is the loudest animal on Earth, capable of producing calls that reach 188 decibels and can be detected hundreds of kilometers away. The bloop was estimated, based on the distances at which it was detected and the acoustic properties of the SOFAR channel, to be far louder than any blue whale call ever recorded. Whatever made it, if anything biological made it, would have to be vastly larger than any animal currently known to exist. This was the opening that popular imagination needed. For years, the bloop circulated online and in media coverage as evidence for the existence of a giant, unknown creature living in the deep ocean, something larger than any whale, large enough to produce an acoustic event detectable across an ocean basin, lurking undetected in the unexplored depths. The Cthulhu hypothesis, named for H.P. Lovecraft's fictional deep-sea entity, was invoked frequently enough that NOAA scientists eventually felt compelled to address it directly in public communications. Their answer, when it came, was more measured than the speculation that had preceded it, but not entirely satisfying. In 2012, scientists revisited the bloop recording using updated analytical tools and a growing database of acoustic signatures from Antarctic ice events. Their conclusion was that the bloop was almost certainly caused by ice quakes, the sound produced by large masses of ice fracturing and moving in Antarctica, transmitted through the Sofar Channel across thousands of kilometers. The shape of the bloop's frequency contour, when compared with recordings of earthquakes made in the years since the original detection, matched closely enough to make this the leading and now widely accepted explanation. Almost certainly. Closely enough. Scientists choose their language carefully. When the literature says almost certainly, it means the evidence points strongly in one direction, but the case cannot be called definitively closed. When it says closely enough, it means the match is convincing but not perfect, that there are features of the original recording that are not fully accounted for by the icequake hypothesis, features that remain to be explained. The bloop is probably explained. The mechanism is probably icequakes. But the exact event, the exact location, the exact sequence of glacial processes that produced an acoustic event of that particular amplitude and profile, these details remain uncertain. The bloop may be in the solved column. The pencil mark is faint. In 1997 and 1999, the same period when the upsweep and the bloop were being identified and named the hydrophone network, detected several other signals that proved more resistant to explanation. In 1999, a recording from the northeastern Pacific captured a sound that did not fit any known geological or biological template. It was low in frequency and long in duration, much longer than the bloop, sustained over a period of several minutes in a way that resembled a continuous geological process more than a discrete acoustic event. But its structure was not consistent with any standard seismic signature. It repeated, appearing in the record on multiple occasions, separated by intervals that were not random, not the irregular spacing of geological events, but something more periodic, more deliberate feeling. Analysts named it the slowdown for the way the sound's frequency gradually decreased over its duration. The slowdown has no confirmed explanation. It is not volcanic in any recognizable sense. It is not seismic in the standard way that term is used. It is not biological. No known animal produces sounds in the frequency range and duration profile that characterize the slowdown. It simply exists in the archive, flagged and named and periodically reanalyzed without a source. The same year, a different signal appeared in recordings from the South Pacific. Shorter and more intense than the slowdown, complex enough in its internal structure that analysts spent considerable time systematically ruling out candidate explanations before concluding that none of them fit. When they rendered a signal on a spectrogram, the visual representation of acoustic energy as a function of frequency and time, it appeared as a long, narrow, nearly horizontal trace. A line moving across the display as if something were traveling along a fixed path at constant speed. They named it the train. What is traveling? Where does it go? After more than 25 years of occasional revisitation, the train remains without a confirmed source. But of all the unexplained sounds in the ocean's acoustic record, none has attracted more sustained scientific attention, more genuine puzzlement, or more unexpected emotional resonance than a signal first detected not in 1997, but earlier in 1989 and tracked with interruptions for more than 3 decades since. In 1989, an acoustic recording from the northeastern Pacific contained something that was unambiguously biological. The frequency structure, the internal modulation, the way the signal varied over time, all of it was consistent with an animal producing a vocalization. Whatever was making the sound was alive. Whatever was making the sound was large. The acoustic properties of the signal were consistent with a large baleen whale, an animal in the size class of blue whales or fin whales, using its vocal apparatus to produce a structured call that propagated through the SOFAR channel. But the frequency was wrong. Blue whales call at frequencies between roughly 10 and 20 hertz. Fin whales call at around 20 hertz. The calls of large baleen whales in general fall below 40 hertz. This is the frequency range these animals have evolved to use, a range that propagates efficiently through the SOFAR channel, and that the auditory systems of other members of their species are tuned to receive. This signal was at 52 hertz, higher than any known species of large baleen whale, high enough that it fell outside the frequency range that any known whale could hear, and yet structured in a way that was unmistakably biological, not random noise, not geological tremor, not any known physical process, a vocalization, a call, something trying in the only way it knew how to communicate. They called it the 5-2 hertz whale. It moved. From year to year, as the tracking continued through the 1990s and into the 2000s, the source of the 5-2 hertz signal migrated through the North Pacific in patterns consistent with the seasonal migrations of large baleen whales moving north in summer, south in autumn, covering distances that only large cetaceans routinely travel. It changed its calling frequency slightly over the years, in a gradual drift consistent with the kind of long-term acoustic changes that researchers have documented in other whale populations. It behaved in every way that acoustic tracking could assess, like a whale, but no one has ever seen it. Not once, in more than 3 decades of tracking, has anyone identified a physical animal, a specific individual, photographed and cataloged that corresponds to the source of the 5-2 hertz signal. The North Pacific is not unmonitored. Research vessels have worked those waters for decades. Whale populations have been surveyed, tagged, photographed, biopsied. Acoustic tracking data from the 5-2 hertz whale has been used to constrain its likely location on numerous occasions. No match has been made. The most widely discussed hypothesis is that the 5-2 hertz whale is a hybrid, the offspring of a blue whale and a fin whale, 2 species that are known to interbreed occasionally in the wild. A hybrid between these two species might have vocal anatomy intermediate between the two parents, producing calls at a frequency that falls between the characteristic ranges of blue whales and fin whales and landing, by genetic misfortune, at 52 Hz. This would explain the anomalous frequency. It would also explain why the animal has never been visually confirmed. Hybrid whales are rare. They look somewhat unusual compared to either parent species, and an observer encountering one in the open ocean might not recognize it as distinct from either. Another hypothesis is that the 52 Hz whale is a single malformed individual, a blue whale or fin whale, with an anatomical abnormality affecting its vocal tract, causing it to produce calls at an unusual frequency. This would be consistent with the apparent singularity of the signal during the years when only one source was detected. In 2010, researchers began to detect multiple signals in the 52 Hz range, not one source, but several, spread across different regions of the North Pacific. This complicates both leading hypotheses. Individual malformations are rare. Multiple individuals producing similar anomalous calls in the same frequency range across the same ocean suggests something more systematic, a characteristic that is shared. That might indicate a small population with a consistent acoustic signature that has never been visually documented. A population of large animals in the Pacific Ocean calling continuously for decades that science has tracked acoustically and never seen. In an ocean where 95% of the volume has never been directly observed, this is not impossible. It is, in fact, the kind of thing that the ocean's opacity makes entirely conceivable. And calling at 52 Hz in a world where no other animal communicates at that frequency means that every signal this animal sends travels perfectly through the SOFAR channel, reaches the auditory systems of every large marine animal in its path, and it conveys nothing. Not because the signal is weak, because the signal is at the wrong frequency, because the rest of the ocean is simply not built to receive it. Whatever this animal is, it has spent its entire existence calling into a silence that is not the absence of listeners, but the absence of listeners who can hear. This is what the ocean's acoustic record contains. Not just unexplained geological sounds, not just anomalies in the noise. A living animal or several calling continuously for decades in a frequency that nothing else in the ocean can perceive. And we found it because we happened to be listening. In 2014, a research team studying seismic activity in the Indian Ocean noticed something unusual in their data. They had been monitoring the region for earthquake activity along the mid-ocean ridge system, the chain of underwater mountains running through the middle of the Indian Ocean where tectonic plates are slowly spreading apart, and magma from the mantle periodically erupts onto the seafloor. This is a geologically active region. Earthquakes and volcanic events occur regularly. The team had been logging acoustic signals consistent with seismic activity and cross-referencing them with data from the Global Seismic Monitoring Network to identify specific events. Something in the cross-referencing did not work. A series of acoustic signals that the team had classified as geological events, low frequency, high energy, consistent in profile with seismic tremor, could not be matched to any event in the seismic record. The signals had the right frequency range. They had the right duration. Their acoustic profiles looked geological. But when the team tried to identify the specific earthquakes or volcanic events that should have produced them, nothing was there. The seismic network had not recorded any event at the time and location implied by the acoustic data. The team spent months working through the discrepancy. They checked instruments. They reviewed methodology. They looked for errors in their propagation models, the calculations that estimated where a sound had originated based on when it arrived at different sensors. They found nothing wrong with their process. Eventually, they found a different kind of answer. The signals were biological. They were being produced by pygmy blue whales, a subspecies of blue whale found in the Indian Ocean, vocalizing at frequencies low enough and in patterns regular enough that the automated classification systems the team had had to categorize them as seismic events rather than animal calls. The whales had been hiding acoustically inside the noise of the earth itself. Their voices had been mistaken for earthquakes. Their migrations had been logged as tectonic activity. For years, no one knows precisely how many whale calls had been stored in seismic databases as geological events. This is the moment that restructures everything. If the calls of a known species, pygmy blue whales, well documented, extensively studied, with a known acoustic profile, can be misclassified as earthquakes by competent researchers using appropriate methodology, then the assumption that we understand the ocean's acoustic record is much weaker than it appears. The catalogs we have built are organized around signals we already know. They are built from the patterns of known sources. They have been constructed by researchers looking for specific things. They do not have a category for signals that combine features of known categories in unexpected ways, or for signals from sources that have not yet been described, or for acoustic events that fall into gaps between established templates. The archive contains more than the catalogs reflect, not because anyone has been careless, because the ocean is larger than our models of it. In 2023, a research team applied machine learning tools to historical recordings from the Pacific Hydrophone Network, recordings that had been collected over decades and analyzed for specific known signals, but not subjected to systematic, wideband pattern recognition. The automated analysis identified a class of acoustic signals that had been present in the recordings for years without being noticed. Not because the signals were faint, because their structure did not resemble any pattern the previous generation of analysis tools had been designed to find. The signals were coherent, meaning they were structured, not random. They repeated across multiple recording sessions at different sensors. They were not geological in any recognized sense. They were not consistent with any known biological species. They were not consistent with any known human-made acoustic source. The team published a preliminary report. They did not claim to know what the signals were. They identified them as anomalous, noted that they were inconsistent with all known source categories, and flagged them for further analysis. As of the preparation of this video, no follow-up publication has appeared. The signals remain unclassified and unexplained. This is how the frontier of ocean acoustics actually looks. Not dramatic announcements of discovered monsters or confirmed mysteries definitively solved, papers that note anomalies, datasets that grow, questions that stay open for years while researchers work through the implications of what they have found, wait for better tools, and return to the problem when the analytical landscape has changed enough to make a new approach possible. The archive is not static. It is being revisited constantly, and what it yields depends on the tools and frameworks brought to it. Each generation of analysis reveals things the previous generation missed. The signals that are anomalous today may be explained tomorrow, or they may not be, and new anomalies will emerge from the same data that previously appeared to contain nothing unexpected. The ocean's acoustic record is not a fixed inventory. It is a resource whose full contents are not yet known, sitting in databases, waiting for the right questions. To understand the context in which the unexplained sounds exist, why they matter beyond their intrinsic scientific interest, it is necessary to understand what has happened to the ocean's acoustic environment over the last century. The ocean that sources began recording in the 1950s was acoustically different from the ocean that exists today. Not fundamentally different. The SOFAR channel was the same, the physics was the same, the biological communities were largely the same. But in one critical dimension, it was measurably, significantly quieter. In the mid-20th century, global shipping traffic was a fraction of what it is today. Commercial vessels were present in the major ocean basins. The Atlantic and Pacific trade routes had been established for centuries, but their density was lower, their engines were less powerful, and the aggregate acoustic footprint of maritime commerce was, compared to the present, modest. The low-frequency band, the range of frequencies between roughly 10 and 500 Hz, which includes the SOFAR channel's optimal propagation frequencies and the communication range of large whales, had a noise floor that reflected primarily geological and biological sources. Over the following decades, this changed. Global shipping expanded dramatically with the growth of international trade. Container ships grew larger, more numerous, and more powerful. Tanker traffic increased. Offshore drilling introduced new sources of low-frequency noise in previously quiet regions. Military sonar exercises added intense acoustic events to the ocean's acoustic environment on a regular basis. The aggregate effect of all these sources, accumulating year by year over decades, was a systematic rise in the ambient noise level of the world's oceans in the low-frequency band. The numbers are stark. In the major ocean basins, the North Atlantic, the North Pacific, the shipping corridors of the Indian Ocean, ambient noise levels in the low-frequency band have risen by approximately 10 to 15 decibels over the last 50 years. Decibels are a logarithmic scale. A 10 decibel increase represents a 10-fold increase in acoustic intensity. In some of the world's most heavily trafficked ocean regions, the low-frequency acoustic environment is now 10 times more intense than it was when systematic monitoring began. For animals that rely on sound for communication and in the ocean, this means almost everything of significance, from large whales to fish to crustaceans to cephalopods. This is not a background change. It is a transformation of the sensory environment in which these animals have evolved, and to which their biology is tuned. A blue whale calling at 20 Hz in the North Atlantic today is producing a signal that must be detected above a noise floor that, in some regions and at some times, is already at or approaching the level at which the signal would normally be detectable at long range. The call still travels. The physics of the SOFAR channel still works. But the distance over which the call can be heard, the range at which another blue whale can detect it above the background, has decreased. By how much? The estimates depend on the specific region, the local shipping density, the time of day, the season. In the worst cases, researchers studying this question have estimated that the effective acoustic communication range of large baleen whales in the North Atlantic may have declined by as much as 90% compared to the pre-industrial baseline. A call that could once propagate across an ocean basin and be detected by conspecifics at a range of hundreds or thousands of kilometers can now, in some regions, be detected only within a fraction of that range. The whales did not evolve for this. The ocean they adapted to the acoustic environment that their low-frequency calls were shaped by evolution to exploit is no longer the ocean they inhabit. The SOFAR channel that blue whale calls were tuned to propagate through has not changed. The noise that fills it has. The animals are carrying an acoustic inheritance adapted to a world that, in this one respect, no longer exists. Whether and how this affects whale populations is an active and contested area of research. The causal chain from acoustic masking to behavioral disruption to population-level effect is long and complicated. Establishing that a population is declining because of noise rather than because of any of the many other stressors these animals face requires the kind of long-term, well-controlled studies that are extremely difficult to conduct on animals that range across ocean basins. The research is ongoing. What is not in question is the physics. The noise is real. The masking is real. The reduction in effective communication range is real. The acoustic environment that these animals inhabit has changed in measurable ways within the lifetimes of individual animals alive today. And while this transformation has been happening while the low-frequency noise floor of the major ocean basins has been rising, making the ocean acoustically louder and harder to understand, the unexplained sounds have continued to arrive at the hydrophone network. The upsweep has continued its seasonal rhythm. The 5-2 Hertz whale has continued to call. New anomalies have appeared in the archive. The ocean has continued to produce acoustic events that do not fit the catalog. We are trying to understand an ocean that is simultaneously becoming harder to understand. We are building better instruments, while the signal-to-noise ratio in the most important frequency bands gets worse. We are deciphering the acoustic record of a quieter past, while the present ocean fills with noise we generate. There are still quiet places in the Southern Ocean, far from shipping lanes and far from any coastline, in waters that have not yet been transformed by the acoustic footprint of industrial civilization. Hydrophones pick up an acoustic environment that is close to what the entire ocean once sounded like. Ice, distant seismicity, biology, the sounds that the ocean makes when nothing human is listening. These recordings are extraordinary. they are also increasingly rare. The noise continues to spread. The quiet retreats. And somewhere in the distance that separates the noise from the silence, sounds travel that have not yet been recorded, and questions accumulate that have not yet been asked. There is a signal that the entire Earth produces continuously, and for decades, science did not know it existed. It occurs at frequencies well below the threshold of human hearing, below the range of the lowest notes on any musical instrument, below the frequencies that any acoustic device designed for human listening can register. It propagates not only through the ocean, but through the solid crust of the planet itself. Every seismic monitoring station on Earth records it constantly. It appears in the data as a faint, persistent, slightly rhythmic component of the background signal, oscillating at roughly one cycle every 5 to 10 seconds. For decades, seismologists noticed this component in their data and categorized it as instrument noise. It was too regular to be random geological activity. It did not look like any known type of seismic signal. The obvious interpretation was that something in the recording equipment was producing a consistent artifact, some vibration or electrical interference in the sensor or the amplifier that appeared in the data as a systematic, low-frequency oscillation. It was not instrument noise. In the 1990s, seismologists working on the problem demonstrated that the signal was real, that it was present in recordings from instruments across the globe, that its properties varied with location and season in ways consistent with an environmental source rather than a systematic artifact, and that its origin was the ocean. Specifically, it is produced by the interaction of ocean waves with the seafloor across the world's continental shelves. As surface waves travel across shallow water, they generate pressure fluctuations that propagate downward and interact with the ocean bottom. These interactions produce seismic waves that travel through the crust of the Earth and can be detected by sensitive instruments anywhere on the planet. The signal is continuous because ocean waves are continuous. It varies seasonally because wave heights and periods vary with season and storm patterns. It is present everywhere because the ocean surrounds the continents and the continental shelves extend around the entire globe. The planet is vibrating at the frequency of its ocean. This is the hum that the Earth produces, not the hum of electromagnetic fields or the hum of geological processes, but the hum of water in motion, the mechanical consequence of waves that have been rolling across ocean surfaces since the oceans formed, transmitted through the seafloor and propagating through the solid earth as a continuous infrasonic drumbeat. The signal was always there. It was present in every seismic recording ever made. The instruments were always sensitive enough to detect it. What was missing was not data. What was missing was the recognition, the willingness to look at something that appeared to be instrument artifact and ask whether it might instead be phenomenon, whether the background might contain signal, whether noise might be information. This is the most important lesson in the history of ocean acoustics, and it repeats in every chapter of the story. The SOFAR channel was present in the ocean before anyone knew to look for it. Sounds had been traveling through it for hundreds of millions of years before a military experiment accidentally demonstrated its existence. Blue whale calls had been logging as seismic events in research databases before anyone thought to check whether geological signals and biological signals might be acoustically indistinguishable. The microsysmic hum of the ocean had been recorded by every seismograph ever built before anyone recognized what it was. In each of these cases, the information was present. It was in the data. The instruments had captured it faithfully without understanding what they were capturing. The mystery was not in the ocean. The mystery was in the gap between what the instruments recorded and what the researchers understood. How many such gaps remain? The archives of ocean acoustic data collected over the last 80 years contain recordings that have never been subjected to the analytical methods that now exist. Not because the researchers who made those recordings were negligent. They analyzed what they were looking for and found it and published the results. But every recording captures everything that arrives at the sensor, not only the signals the researchers were designed to detect. The rest is in the data. It has always been in the data. Machine learning systems trained on known signal types are now being applied to these archives, searching for patterns that previous analysis missed. The results, consistently, are that previous analysis missed things. Coherent signals, repeated across multiple sensors, not matching any known source category. Patterns in the noise that look like signal when the right tools are applied. Structures in the acoustic record that were invisible to previous generations of analysis and are now tentatively becoming visible. Some of these will turn out to be explainable. Some will turn out to be known phenomena that were not recognized in an unfamiliar form. Some will be new. The ratio between these categories is not yet known, because the work is ongoing. But the history of every previous application of improved analytical methods to ocean acoustic data strongly suggests that the fraction that is genuinely new and unexplained will not be zero. This is not a claim that the ocean harbors unknown monsters or civilizations or phenomena beyond the reach of science. It is a claim grounded in the actual history of ocean acoustics, that the ocean is sufficiently large, sufficiently complex, and sufficiently poorly monitored that it consistently produces acoustic phenomena that exceed the capacity of current models to account for them. It has always done this. There is no reason to think it will stop. The ocean produces approximately 11 million distinct acoustic events per day. This is an estimate extrapolated from monitoring coverage to the full ocean volume, carrying the uncertainty of any such extrapolation, but consistent across different methodologies. Of these 11 million daily events, the fraction captured by any monitoring instrument is less than 1%. The fraction of the captured data that is analyzed by human experts is a small subset of that. The fraction that is analyzed by any method capable of detecting unknown signal types is smaller still. The rest is lost. Not because it is inaccessible in principle. The physics of the SOFAR channel means that sounds produced almost anywhere in the ocean can potentially reach sensors that are listening for them. But because the sensors are not listening everywhere, and the analysis is not looking for everything, sounds travel across ocean basins, arrive at hydrophones, are recorded, and sit in databases unexamined. Or they arrive at regions without any monitoring at all and simply fade, becoming part of the ambient noise of a planet in constant acoustic motion, carrying in their dissipation the information about their source that will never be extracted. What is happening in the unmonitored regions, the Southern Ocean, the deep Indian Ocean, the Hadal trenches below 6,000 meters, where no acoustic monitoring has ever been conducted, is completely unknown, not almost unknown, not poorly characterized, unknown. The data does not exist. The question of what those regions sound like, what acoustic events they produce, what signals they might contain that would be significant to science, cannot be answered because no one has listened. This is the condition of ocean acoustic science at the beginning of the 21st century. A vast acoustic environment that has been operating for billions of years, monitored in a fraction of its volume, analyzed with methods that are improving but remain inadequate to the scale of the task, and consistently, in every decade of systematic monitoring, found to contain phenomena that the previous generation of scientists did not anticipate. The 5-2 Hertz whale is calling right now. Somewhere in the North Pacific, in cold, dark water, something is producing a sound at 52 hertz that has been traveling through the SOFAR channel and arriving at recording instruments for more than 30 years. The sound is in the data today, as it was yesterday, as it will be tomorrow. The question of what produces it, what animal, what mechanism, what history, remains open. The ocean is not keeping this secret deliberately. It cannot keep secrets. It carries every sound that enters it, propagates every acoustic event according to the physics of water, delivers every signal to every sensor in range. The limitation is entirely on our side. The inadequacy of coverage, the incompleteness of analysis, the finitude of human attention applied to an environment of planetary scale. We are at the beginning of understanding what the ocean sounds like. Not the end, not even the middle. The unexplained sounds are the ocean's way of telling us, not in any language addressed to us, not in any signal designed to be heard, that the question is much larger than the answer we have so far assembled, that the archive contains more than we have read, that the unmonitored regions contain more than we have imagined, that the history of every previous attempt to characterize this acoustic environment has been followed by the discovery that the characterization was incomplete. The water is deep. The sounds are real. The questions are open. And somewhere, in the unmonitored dark, something is making a sound right now that no instrument has ever captured traveling outward through the SOFAR channel at 1,500 meters per second, carrying encoded in its frequency and its structure some information about what made it and where it came from, moving through water that has carried sounds like it for 4 billion years towards sensors that may or may not be sensitive enough to detect it, toward analysts who may or may not have the tools to understand what they are hearing. It will travel until it fades. It will become part of the background. It will join the accumulated acoustic history of a planet that does not keep records for minds that were not there to receive them. Unless something is listening, if this journey moved something in you, consider subscribing to Sleep on Deep. Every week, we descend a little further. The ocean is waiting. Consider what it means that the 5-2 Hertz whale has been calling for more than 3 decades and has never been seen. Not that it has been looked for and not found, though this is also true and significant in its own right. But that it has been tracked year after year, its migrations followed through acoustic monitoring, its location constrained to regions of the North Pacific where research vessels regularly operate, whale surveys regularly occur, and marine mammal observers regularly scan the water from the decks of ships doing other work. And in all of that time, in all of that incidental observation, no one has ever reported seeing an animal that corresponds to the source of the 5.2 Hz signal. This is unusual. Large baleen whales surface to breathe. They are visible when they do. They are large enough blue whales, average around 25 meters in length, and can exceed 30, that a whale at the surface of the ocean is not easily missed by an observer in the area. The North Pacific is not unobserved water. It is crossed by shipping lanes and research routes, and the paths of fishing fleets, and the transects of whale survey programs that have been operating for decades. And yet, the most likely explanation remains the hybrid hypothesis, a blue whale, fin whale hybrid that looks unusual compared to either parent species and has therefore been observed without being recognized as distinct. This is scientifically plausible. Hybrid cetaceans have been documented. They exist. They are rare, but not impossibly rare. A single hybrid individual, or a small number of them, could plausibly have migrated through the North Pacific for 3 decades without anyone noting them as unusual enough to report in any context that would have reached the researchers tracking the acoustic signal. The least likely explanation, scientifically, is the one that the popular imagination reaches for first. An entirely unknown species of large whale, moving through one of the world's better studied ocean regions, invisible to the surveys and observers that regularly work there, calling at a frequency that places it acoustically outside every category of animal currently described by science. The least likely. Not impossible. The ocean has produced surprises of this magnitude before. The coelacanth, a large, distinctive fish belonging to a lineage thought to have been extinct for 65 million years, was discovered alive in 1938 when a specimen was caught by a fisherman off the coast of South Africa. The megamouth shark, a filter-feeding species reaching over 5 meters in length with an enormous, distinctive appearance unlike any other shark, was not discovered until 1976, when one became entangled in a sea anchor deployed by a U.S. Navy vessel in the Pacific. The Omuraz whale, a species of baleen whale in the same family as blue and fin whales, was formally described only in 2003 based on specimens caught by Japanese research vessels, and was not observed alive in the wild until 2015. These are large animals, distinctive animals, animals that, once observed, are clearly identifiable as distinct from known species. And all of them were unknown to science until recent decades, despite inhabiting ocean regions that were not entirely unmonitored. The ocean is large. The fraction of it that is under regular observation at any given time is small. The probability of any specific unknown large animal being observed and its observation being reported to the right researchers is lower than intuition suggests. This does not mean the 5.2 Hz whale is an unknown species. The hybrid hypothesis remains more parsimonious. But the fact that the question is still open, that 3 decades of acoustic tracking have not been resolved into a definitive biological identification, tells us something important about the limits of what acoustic monitoring alone can establish. We can hear it, we cannot see it. And in an ocean that is far more thoroughly acoustically monitored than it is visually observed, this gap between what we can detect through sound and what we can confirm through direct observation is not a minor technical limitation. It is a fundamental constraint on what can be known. The ocean's biology extends beyond what can be directly observed. Sound tells us things that observation cannot, but sound also raises questions that observation has not yet answered. The 5.2 Hertz whale is the most poignant example of this tension, an acoustic signature tracked for decades, attached to a biological reality that science has not been able to confirm. But it is not the only example. There are biological sounds in the ocean's acoustic record that have not been matched to any identified species. There are calling patterns from deep water regions that suggest the presence of animals that have never been described. There are acoustic events in recordings from poorly monitored ocean areas that look biological structured, repeated, modulated in ways that suggest intentionality of the kind associated with animal communication and that remain unattributed. How many unknown species are producing sounds in the ocean? The question cannot be answered from acoustic data alone, but the existence of sounds that do not match any known species sets a lower bound, at least one, probably more. What are they? Where do they live? What are they communicating? In calls that have never been heard by any member of their own species, or that have been heard and responded to in ways that neither the animals nor any human has understood. The ocean contains these questions. It has always contained them. It will contain them long after any particular line of research has moved on to other problems. The questions are patient in the way the ocean is patient, not aggressive, not demanding, just present, sitting in the acoustic record, waiting for methods adequate to address them. There is a community of organisms in the ocean that is among the largest on Earth by total biomass, performs one of the largest daily migrations of any living system, and was discovered almost entirely by accident. It lives in the deep ocean during the day, at depths between roughly 200 and 1,000 meters, in the dimly lit or completely dark waters below the sunlit surface zone. At dusk, it rises. Not all at once, not in a coordinated movement that any individual organism orchestrates, but in a collective upward drift, driven by the same stimulus of the fading of light that triggers similar responses in countless species across the full diversity of ocean life. By night, it is near the surface, feeding in the productive upper layers of the ocean. By dawn, it descends again, retreating to depth as light returns. This migration, occurring every day in every ocean, involving billions of individual animals, representing hundreds of species of fish, squid, crustaceans, and other invertebrates, is one of the most significant biological events on the planet. The amount of carbon that these organisms transport from the surface to the deep as they migrate. As they feed at the surface, and respire at depth and die at depth and become food at depth is a major component of the ocean's biological carbon pump, one of the primary mechanisms by which the atmosphere's carbon dioxide is transferred to long-term storage in the deep ocean. It was discovered because of sonar. During and after World War II, naval operators using early sonar equipment to detect submarines noticed that their instruments were showing a false seafloor, a layer of acoustic reflectivity at depths between a few hundred and 1,000 meters that seemed to be a solid surface, but clearly was not. When depth-sounding surveys were conducted and found nothing physical at those depths, and when the apparent depth of the layer was observed to change over time, rising at dusk, deepening at dawn, the explanation became clear. The reflective layer was biological. It was composed of organisms dense enough and with internal structures acoustically reflective enough that the aggregate of billions of them in a layer produced a sonar return comparable to the seafloor. They called it the deep scattering layer. Without sonar, without the acoustic technology that was developed for military purposes and applied to ocean science, the deep scattering layer would have remained invisible. It cannot be observed from the surface. It cannot be seen at depth. The organisms that compose it are individually small, dispersed across hundreds of meters of depth and thousands of square kilometers of ocean area, and mostly live in conditions of near or complete darkness, where visual observation is impossible regardless. The only way to know it is there, without physically entering the water and sampling it, is to send sound into the ocean and interpret what comes back. This is what acoustic research does. Not just detect anomalous sounds and try to explain them. Not just monitor the calls of known species, but reveal the structure and biology of an ocean that is opaque to every other method of remote observation. Sound penetrates the ocean in ways that light cannot. Sound returns information from depths and distances that direct sampling cannot reach. Sound is the primary tool through which the interior of the ocean, the vast, dark volume that constitutes most of the ocean's space and most of its biological community, can be studied at all. The deep scattering layer is just one example. The distribution of fish schools throughout the water column, their density, their depth, their daily movements is studied primarily acoustically. The migration routes of large marine mammals across ocean basins are tracked primarily acoustically. The geological activity of mid-ocean ridges, seamounts, and submarine volcanoes is monitored primarily acoustically. The circulation patterns of the deep ocean, the slow, cold currents that carry water from the poles toward the equator and back, over timescales of centuries, are characterized partly through acoustic methods that measure sound speed, which depends on temperature across ocean-scale distances. Without acoustic research, the ocean interior would be nearly as unknown to science as it was before the development of oceanography as a discipline. The fact that we know as much as we do about what happens below the ocean surface, the biology, the geology, the physics, is largely a consequence of the fact that sound travels in water in ways that no other energy source matches. And the fact that we keep finding unexplained things, the upsweep, the bloop, the train, the slowdown, the 5.2 Hertz wave, the unclassified signals in the 2023 machine learning analysis is not evidence that acoustic research has failed. It is evidence that acoustic research has succeeded well enough to reveal how much more there is to find. Each anomaly is a data point, not about the ocean's inscrutability, but about its depth. The depth of complexity and biological richness and geological activity that exists in a volume of water so large that the human mind has no intuitive framework for grasping it. The ocean floor alone, the seafloor beneath the water, the surface on which sediment accumulates and geological features rise and volcanic activity occurs, covers more area than all the continents combined. The volume of ocean water above that floor is sufficient to submerge the entire surface of the earth, land and sea alike, to a depth of more than 2 kilometers. The sheer scale of what we are trying to understand through instruments that sample a fraction of its surface and a tinier fraction of its volume is the primary reason that so much remains unknown. Not inscrutability, scale. There is something that happens to your perception of the ocean when you understand how sound moves through it. Before this understanding, the ocean is a surface. It is what you see from a beach or a boat, the boundary between the world you live in and a world you can enter only briefly, shallowly, and at the cost of significant equipment and preparation. The ocean is what waves do to the shore. It is what weather forms over. It is the medium through which ships travel and fish are caught and submarine cables are laid. It is enormous, certainly, and incompletely known, but it is known enough to navigate and exploit and to treat as a background condition of a planet whose surface happens to be mostly water. After this understanding, the ocean is something else. It is an acoustic volume. It is a space in which every event, every whale that calls, every iceberg that calves, every volcanic vent that releases gas, every ship that crosses produces sound that travels at 1,500 meters per second through a medium that carries it with almost no loss, channels it through the SOFAR channel across ocean basins, and delivers it, hours later, to instruments on the other side of the world. It is a space in which the past is still present, in the form of sound, still traveling. A geological event that happened this morning is still audible, acoustically, to sensors thousands of kilometers away. The call of a whale made an hour ago is still propagating outward through the water. The ocean is not just the present state of the water and everything in it. It is the acoustic history of the last several hours of everything that has happened across its entire volume, still in transit, still carrying information, available to any instrument sensitive enough to receive it. This is a different kind of space than any other environment on Earth. Land does not do this. Sounds dissipate quickly in air, and the landscape is acoustically opaque beyond a few kilometers. The atmosphere is acoustically complex, but bounded and relatively thin. Space is, for practical purposes, acoustically silent. Only the ocean combines the properties of a large enclosed volume, an efficient acoustic medium, and the presence of active sources, geological, biological, the physical that produce sounds across a frequency range spanning many orders of magnitude continuously throughout a space large enough to require hours for any signal to cross. The ocean is an acoustic machine, and we are only beginning to understand what it is saying. Most of what it is saying we will never hear. The sounds produced in unmonitored regions will fade before any instrument captures them. The sounds produced below the sensitivity threshold of current hydrophones will disappear into the background noise. The signals in the archive that have never been analyzed will sit in databases until the storage media fails or the institutions maintaining them lose funding, or the relevance of the old recordings is simply overtaken by the volume of new ones. The vast majority of the ocean's acoustic output in every second of every day since the ocean formed has been and will continue to be produced, propagated, and dissipated without ever entering any human record. This is not a tragedy. It is simply a description of the relationship between a finite scientific enterprise and an infinite natural phenomenon. The ocean does not need to be understood. It does not produce its sounds for any audience. The fact that some of those sounds reach instruments that are connected to minds capable of asking what they mean is, from the ocean's perspective, irrelevant. From our perspective, it is everything. We are animals with auditory systems evolved to perceive a narrow slice of the acoustic world, living on the surface of a planet whose largest environment communicates primarily in frequencies our ears were not built to detect. At distances, our intuitions were not built to comprehend through a medium that is as alien to our physiology as the vacuum of space. The instruments we have built extend our perception into this environment imperfectly, partially, but genuinely. They give us access to sounds that would otherwise be entirely beyond us. And in those sounds, we keep finding things that surprise us, that exceed our models, that require us to revise our understanding of what the ocean is and what lives in it and what happens in it and what it does. The 5-2 Hertz whale has been calling for more than 35 years. The upsweep has been rising and falling with the seasons for more than 3 decades. Somewhere in the Pacific, in recordings that have not yet been fully analyzed, there are signals that the 2023 machine learning study identified as anomalous and that remain unexplained. Somewhere in the unmonitored Southern Ocean and the unmonitored Hadal Trenches and the unmonitored deep Indian Ocean, sounds are being produced right now that no instrument has ever captured. The ocean is speaking. It has always been speaking. The only question that ocean acoustic science is actually trying to answer is whether we will learn in the time that we have and with the tools that we can build enough of its language to understand what it is saying. We have learned some. We keep learning more. The archive grows. The analysis improves. The coverage extends. The frontier recedes. And the ocean keeps producing sounds we cannot explain. Right now, as it has been for hours, as it will continue to be for hours, more a sound is traveling through the SOFAR channel somewhere in the Pacific Ocean. It entered the channel at a depth of around 800 meters. At the location where the ocean's thermal structure creates the refractive conditions that trap acoustic energy and channel it horizontally rather than allowing it to spread in 3 dimensions. It entered traveling at nearly 1,500 meters per second, carrying in its frequency and its amplitude and its internal structure some encoded information about the process that produced it, what it is, where it came from, whether it was made by geology or biology or some combination of the two that science has not yet characterized. It has been traveling for several hours. In those hours, it has crossed a distance that would take a commercial aircraft most of a day to fly several thousand kilometers of open ocean, deep water, no continental shelf, no major topographic feature to scatter it or redirect it. The SOFAR channel has carried it faithfully, bending it back toward the channel axis whenever the physics of refraction would otherwise allow it to escape, keeping it on course, keeping it alive in the water. At some point in the next few hours, it will reach a hydrophone, or it will not. There are more regions without monitoring than regions with it, and the probability that any given signal reaches a listening instrument before it fades below detection threshold is lower than the probability that it does not. But assume it reaches 1. The hydrophone will record it. The electrical signal from the transducer will be digitized and stored. The recording will join the archive, the vast, accumulating, incompletely analyzed archive of ocean acoustic data that stretches back decades and contains, distributed through its billions of data points, the acoustic history of one of the largest environments on the planet. At some future point, an analyst will examine the recording. They will apply whatever tools our current acoustic classification software, machine learning models trained on a catalog of known signals, spectral analysis, comparison with signals from neighboring sensors. If the sound matches a known source, a whale species, a geological event type, a shipping signature, it will be logged and move on. If it does not match, it will be flagged. It will be examined more carefully. It will be compared with other anomalous signals in the archive. It may be explained by a researcher who recognizes a pattern. It may not be explained and may join the growing collection of signals that are coherent and real and unmatched to any known source. Either way, the ocean does not care. The ocean produced the sound because something in it, geological, biological, physical, produced the sound. The sound traveled because the physics of water caused it to travel. The channel carried it because the SOFAR channel carries sounds. The hydrophone recorded it because that is what hydrophones do. The analyst will examine it because that is what analysts. None of this has anything to do with the ocean. The ocean is water. It is the largest body of water on this planet, 4 billion years old, the origin of all life that exists, the regulator of the climate, the carrier of heat from equator to pole and back, the medium through which the Earth's largest biological communities live out their entire existence. It is doing what it has always done, cycling and circulating and supporting and connecting and, incidentally, transmitting sound with an efficiency and a reach that nothing on the land surface of this planet can match. We are the ones who have decided this matters. We are the ones who built the instruments and trained the analysts and designed the algorithms and wrote the papers. We are the ones who named the upsweep and the bloop and the 5-2 Hertz whale and try to understand what they are and why they are and what their existence tells us about an ocean that we have been trying to know for less than a century. We are the ones who are moved genuinely, scientifically, sometimes philosophically, by the fact that something in this ocean has been calling for more than 30 years at a frequency that nothing else can hear. The ocean is not moved. The ocean is water. But we are not water, and the sounds are real, and the questions are open, and the work of listening continues. And somewhere in the deep Pacific, in cold water under immense pressure, at a depth where no light has ever reached and no human being has ever been, the sound is still traveling. It has been traveling for hours. It will keep traveling. If this journey moved something in you, consider subscribing to Sleep on Deep. Every week, we descend a little further. The ocean is waiting. There is a particular kind of knowledge that comes only from listening for a very long time, not from a single recording, however clear, not from a single expedition, however well equipped, not from a single analysis, however sophisticated, but from the accumulation of years of recordings and the slow emergence, through that accumulation, of patterns that are invisible in any individual sample and only become apparent over time. The seasonal rhythm of the upsweep rising in spring, fading in winter, rising again was not apparent from any single recording. It became apparent only because researchers had access to recordings spanning years and could see the signal repeating with a periodicity that no single observation would have suggested. The gradual shift in the 5-2 Hertz whale's calling frequency over the years, a slow drift downward that some researchers believe reflects the aging of the animal. Others, the acoustic adaptation of an individual to a noisier ocean, was only detectable because the signal had been tracked for decades. The presence of multiple 5-2 Hertz sources in the Pacific, detected in 2010, was only apparent because the archive was long enough and dense enough to allow comparison of signals from different locations across different years. Long-term acoustic monitoring is not a glamorous form of science. It does not produce dramatic announcements on a regular schedule. It produces data, enormous quantities of data, requiring systematic analysis, generating results that are often incremental, a pattern slightly more clear than before, a hypothesis slightly better supported than it was, a question slightly better defined than it was when the monitoring began. The breakthroughs, the moments when the accumulated data suddenly reveal something unexpected and significant, are real, but they are preceded by years of unremarkable data collection that forms the foundation without which the breakthrough would not be possible. The SOSUS archive, when it was open to civilian researchers, contained decades of continuous recordings. The decades were the point. Not any single recording, not any single year. The decades. The continuity. The fact that the same instruments had been listening in the same places for the same period of time that it takes for slow patterns to become apparent and for seasonal and annual cycles to be identified as such. Ocean acoustic science is dependent on continuity in a way that other fields are not. A hydrophone deployed for a year and then recovered tells you what the ocean sounded like for that year. A hydrophone deployed for a decade tells you how the ocean's acoustic environment changed over 10 years, which is a qualitatively different and much more valuable piece of information. A network of hydrophones that has been operating continuously for 30 years tells you things about the ocean that simply cannot be known from shorter records. This creates a problem that is partly scientific and partly institutional. Funding for long-term monitoring programs is harder to obtain than funding for individual experiments with clear timelines and anticipated results. The value of a monitoring program is often only apparent in retrospect after the decades have passed and the patterns have emerged that required those decades to become visible. Funding agencies making decisions in the present cannot see the future patterns that the current data will eventually reveal. They see a program that is collecting data without producing dramatic results, and the temptation is to redirect resources toward research that promises clearer short-term returns. Several important ocean acoustic monitoring programs have been discontinued or reduced over the last 30 years, not because they failed to produce valuable science, but because the institutional frameworks that support science did not adequately value long-term continuity. Gaps appear in the record. Patterns that might have been detectable over an uninterrupted 50-year record are less clear when the record contains gaps. The 5.2 Hertz whale has been tracked with interruptions periods when the monitoring that detected it was not operating, leaving gaps in what is already a sparse dataset. What happened to the animal during those gaps is unknown. The scientific value of continuous long-term monitoring is in some ways inversely proportional to the ease of making the case for it at any particular moment. The case is made by the results, which arrive slowly and are only fully interpretable in retrospect. The decisions about whether to maintain the monitoring are made continuously in the present under the pressure of competing priorities. This tension is not unique to ocean acoustics. It characterizes long-term environmental monitoring of all kinds. But the ocean's particular acoustic properties, the way that sound carries across ocean basins, connecting events in one location to instruments in another, allowing a global acoustic environment to be sampled from a relatively small number of well-placed sensors, make ocean acoustic monitoring unusually valuable relative to the cost and complexity of maintaining it. A hydrophone in the SOFAR channel at a well-chosen location in the Pacific Ocean is, in a very real sense, listening to the entire Pacific, not to every sound, not with equal sensitivity to all directions, but to the acoustic traffic of one of the world's largest ocean basins, in a way that no other monitoring method can approximate. This is a remarkable capability. It is worth maintaining. Whether it will be maintained, whether the funding structures and institutional priorities of ocean science will support the continuity that the science requires, is a question whose answer will become apparent only in the person, long-term records that future researchers will or will not have access to. The ocean is patient. It will continue producing sounds whether or not anyone is listening. The question is whether we will have the long-term commitment to listen continuously enough to hear what it is actually saying, not just the sounds that are detectable in any individual year, but the patterns that only become visible across decades. The upsweep has been rising and falling for more than 30 years. At some point, the pattern will change, will stop, or shift, or transform in some way that reveals something about its source that 3 decades of consistent repetition could not. The change will only be recognizable as a change if the record is uninterrupted. If there are gaps, years when the monitoring was not operating, the change may be attributed to the gaps rather than to the phenomenon. The 5.2 Hertz whale has been calling for more than 35 years. At some point, it will stop either because the individual or individuals producing the signal will die, or because they will shift to a different frequency, or because the source of the signal will be identified and it will no longer be classified as unknown. The end of the signal, or the identification of its source, will be scientifically significant in ways that depend on how much of the signal's history has been continuously recorded. The anomalous signals identified in 2023 through machine learning analysis of historical data will either be explained or they will persist. If they persist, and if monitoring continues, and if the analysis continues to improve, the signals will accumulate more detections, more temporal and spatial coverage, more data to work with. If monitoring is interrupted, the signals will be less well characterized when the question of their origin is eventually addressed. Science is not just about what is discovered. It is about the conditions that make discovery possible. Long-term acoustic monitoring is one of those conditions for ocean science. It is not sufficient on its own. Instruments and analysis and researchers and institutions are all required, but it is necessary. Without the continuity of the record, much of what has been learned about the ocean's acoustic environment could not have been learned. Without the continuation of the record, much of what remains to be learned may never be. The ocean will keep producing sounds. The question is whether we will keep listening. What would it mean to truly understand the ocean's sounds? Not to have cataloged every known source and assigned every recorded signal to a known category. Not to have explained every anomaly in the archive and reduced every unexplained phenomenon to an understood process, but to genuinely understand in the way that a person who has spent decades in the language understands it, not just parsing individual words, but hearing the texture of meaning and rhythm and tone, and the spaces between sentences, what the ocean is saying. It would mean understanding the geological conversation, the continuous exchange of acoustic signals between volcanic activity and tectonic movement and submarine landslides and the slow creep of plates, all producing sounds that travel through the SOFAR channel and arrive at sensors as a complex mixture of overlapping signals from sources distributed across the ocean floor. It would mean being able to read this conversation the way a seismologist reads a seismogram, not just detecting that something happened, but understanding what happened and where and why. It would mean understanding the biological conversation, the calls of whales and dolphins and fish and invertebrates, the acoustic structure of communities and populations and migrations, the way that individual animals use sound to navigate and communicate and find food and find mates, and the way that these individual acoustic behaviors aggregate into the collective acoustic signature of entire ecosystems. It would mean being able to hear a recording from the deep midwater and understand not just that organisms are present, but what species, in what numbers, in what behavioral state, doing what. It would mean understanding the physical conversation the way that the ocean's thermal structure and salinity distribution and current systems shape the propagation of every sound, creating an acoustic environment that is not a passive background, but an active participant in every acoustic event. It would mean having models of acoustic propagation accurate enough that a signal detected at a hydrophone could be traced back to its source with precision not estimated, not approximated, but precisely located and timed. We are far from this understanding. Far not in the sense of being hopelessly distant from it. The progress of the last 80 years has been extraordinary, but in the sense that the distance remaining is much greater than the distance covered. The geological conversation is partially understood in the regions that are well monitored, poorly understood elsewhere. The biological conversation is understood for the species that have been studied intensively, almost entirely unknown for the majority of marine species that produce sounds but have not been characterized. The physical conversation is understood well enough for large-scale propagation modeling, but not well enough for the precision that would allow confident source localization of novel signals. Every anomaly in the acoustic record is a measure of this remaining distance. Every unexplained signal is an indication of how much the current understanding does not capture. The upsweep, the 5.2 Hertz whale, the unclassified signals from the 2023 analysis, these are not embarrassments or failures. They are progress reports. They tell us not that science has stopped working, but that the system being studied is larger and more complex than the current state of science has fully characterized. The ocean has always been larger and more complex than the current state of science has fully characterized. This has been true for every generation of ocean researchers. It will be true for every future generation. The distance between what is understood and what exists to be understood may not close. It may grow as improved methods reveal new layers of complexity that previous generations could not see. This is not discouraging. It is the nature of science confronting a genuinely complex natural system. The goal is not to exhaust the ocean's acoustic complexity to know everything there is to know and have nothing left to discover. The goal is to continue learning to make the catalog of understanding larger and more detailed and more accurate, to reduce the number and size of unexplained phenomena, to build the tools and maintain the continuity of monitoring that makes future discovery possible. The ocean is doing its part. It is producing sounds continuously, as it has for billions of years. It is transmitting them through the SOFAR channel with the fidelity of physics. It is delivering them to every instrument that is placed in the water. The rest is up to us. We have been listening for 80 years. The archive is deep. The questions are many. And the ocean's acoustic output shows no sign of exhausting itself or repeating itself or running out of new things to say. Somewhere, right now, the 5.2 Hertz whale is calling. Somewhere, the upsweep is rising toward its spring peak. Somewhere, in a database that has not yet been analyzed, a signal sits in the archive that will, when someone finally looks at it with the right tools and the right questions, reveal something about the ocean that nobody currently knows. The water is deep. The sounds are real. The questions are open. We keep listening. If this journey moves something in you, consider subscribing to Sleep On Deep. Every week, we descend a little further. The ocean is waiting. The ocean floor, at its deepest points, has never been heard. Not monitored, not recorded, not sampled, heard. In the most basic sense of having any instrument capable of receiving acoustic energy present in those regions. The Hadal Zone, the ocean's trenches, the places that descend below 6,000 meters and reach their maximum depth at just under 11,000 meters in the Mariana Trench, is the least acoustically characterized environment on Earth. Hydrophones have been deployed in some trenches for short periods as part of specific research expeditions. They have found that the acoustic environment at those depths is not silent. It contains geological sounds, biological sounds, and in recordings made in the Mariana Trench in recent years, the sounds of ship engines and the calls of baleen whales traveling through the Sofar Channel from thousands of kilometers away. Even in the deepest place on Earth, human noise has arrived. What else has arrived? What has always been there? What is produced by the geological processes of the trench environment and the biological communities that live there? These questions have barely been approached. The research is fragmentary. The monitoring is episodic. The acoustic environment of the Hadal Zone is, to a degree that is difficult to overstate, unknown. This matters not only because of what might be found there. It matters because the Hadal trenches are geological structures. The boundaries between tectonic plates, the regions where one plate descends beneath another in a process called subduction. Subduction zones are associated with the largest earthquakes on Earth. The acoustic precursors to major seismic events, if they exist, would be most directly detectable in these regions. The geological processes that drive the slow movement of plates producing over millions of years. The current configuration of the continents and oceans produce acoustic signals that travel through the solid earth and into the water column, and would be detectable by instruments in the trenches if those instruments existed. They mostly do not. The Hadal Zone also hosts biological communities that are found nowhere else, organisms adapted to pressures that would instantly kill any surface animal, surviving in complete darkness at temperatures near freezing, feeding on the organic material that sinks from the productive surface ocean above. Some of these organisms have been sampled. Most have not been acoustically characterized. Whether they produce sounds, what those sounds are, whether they contribute to the acoustic environment of the trenches in ways that a monitoring program would find significant unknown. The trenches are the last acoustic frontier of the ocean, in the sense of being the regions least approached by existing monitoring. They are not the only frontier. Much of the Southern Ocean is acoustically undermonitored. Large portions of the Indian Ocean's interior are acoustically undermonitored. The deep Arctic, changing rapidly as sea ice retreats, and shipping routes that were previously impossible become navigable, is entering a period of acoustic transformation that is only beginning to be documented. The ocean's acoustic environment is not fixed. It changes with the climate, with the activity of human civilization, with the slow dynamics of geological processes that operate on timescales of thousands to millions of years. The acoustic environment of the ocean a century from now will be different from the acoustic environment of the ocean today, which is different from the acoustic environment of a century ago. What we capture now, the recordings being made today, the archive being built in the present, will be, for future researchers studying those changes, what the SOSUS archive was for the researchers who first had access to it in the 1990s. Decades of continuous data containing patterns that will only be apparent in retrospect, revealing things about how the ocean changed that no contemporaneous observation could have identified. The sounds that are being recorded today, including the sounds that are not yet understood, are the historical record that future ocean acoustic science will need. The unexplained signals of today may be the explained phenomena of tomorrow, or they may be the starting point for questions that cannot yet be formulated. Either way, their presence in the archive is prerequisite to whatever understanding eventually emerges. This is why the unexplained sounds matter not only as mysteries to be solved, not only as evidence of the ocean's continuing acoustic complexity, but as data points in a long-term record whose full significance will only be apparent across time. The upsweep has been in the record for 30 years. Future researchers will have access to a 40-year record, a 50-year record, a 100-year record, if monitoring continues. The patterns visible in those longer records will tell them things that the 30-year record cannot. What those patterns reveal will depend, in part, on the continuity of the monitoring that connects the present moment to those future records. The ocean's story is long. Human attention to it is short. The task of ocean acoustic science is to extend that attention to maintain the listening across the years and decades that separate a single observation from a meaningful understanding of a system that operates on time scales far exceeding any individual human life or any individual research program. Right now, the hydrophones are listening. The archive is growing. The analysis continues. The ocean is speaking in frequencies below human hearing, across distances beyond human intuition, through a medium alien to human physiology. And in the data, patient and precise, the 5'2" Hertz whale is still calling. If this journey moved something in you, consider subscribing to Sleep on Deep. Every week, we descend a little further. The ocean is waiting.